Click the bell icon to get latest videos from Ekeeda.
Hello friends, how are you? In this particular video, we will learn the high frequency response of CSCE multistage amplifier. Now, as far as high frequency response is concerned, we will just calculate what will be the higher cutoff frequency with respect to multiple RC circuits in my multistage amplifier. Now, in this particular circuit is in front of you. So, first stage comprises of the JFET, where JFET is along with RD, RS, that are nothing but the resistances connected to the drain and source terminal, and the gate terminal resistances R1 and R2 connected with the coupling capacitor CC1 and source resistance, that is R signal, connected with input side. So this is all about the input side. Input is connected to that particular stage, that's why it is called as an input stage. So similarly, this output of input stage is connected through coupling capacitor CC2 to your second stage of BJT, that is of CE mode, and where I will be getting the output from the collector of that particular stage of CE mode, and that's why that stage number 2 is also called as output stage, right? So as far as high frequency response is concerned, we will first analyze whether at high frequency my operation is changing, what will be the effect on my operation as an amplifier as far as high frequency is concerned. So let us understand the fact that if frequency is very high, that means if frequency is tending towards infinity, that it affects your capacitive reactance tending towards zero value. That means all the capacitive reactance becomes short circuited. So will it affect really on my particular circuit as far as CC1, CC2, CE, CS and CC3 are concerned? No, not really. Basically CC1, if it is short circuited, your input is directly connected to your first stage, and your output of stage 1 is directly connected to stage number 2, right? So basically CC1, CC2, CC3, CE and CS are not responsible to calculate what will be the value of FH, that is the higher cutoff frequency. My higher cutoff frequency can be anything, can be infinite as well, but do we really get that particular frequency as an operating frequency for that particular multi-stage amplifier operation? No, not really. This is because there are few more capacitances are there, intrinsic capacitances they are called as, and these intrinsic capacitances when becomes short circuited, they can affect your operation as an amplifier. They will not give you the gain which is required for you as a customer point of view. So let us see that this intrinsic capacitor is nothing but, let's see, this is G1, that is gate 1, this is your drain, that is D1, this is your source, that is S1. So in between gate and drain I will be having capacitance, that is called as an intrinsic capacitance or stray capacitance. Uska namakaran I will do in between gate and drain of first stage. I will say that it's nothing but CGD1. In between drain and source I will say that this is nothing but your CDS1. Similarly, in between gate and source I will be saying that this is nothing but CGS1. Simple, right? So as far as the stage 2 is concerned, I will be getting here, it is base, this is emitter, and this is your collector side. So in between base and collector I will be getting CBC2, right? This is your CCE2, right? And this is nothing but your CBE2, right? As far as all these capacitances are concerned, just concentrate on these green capacitances. So if I'm saying that all the capacitances are getting short circuited, then what will be the effect? Then all the terminals will get shorted, and that is not desirable as far as this amplifier operation with multi-stage circuit is concerned. Okay, so that's why we have to determine up to what particular frequency we can operate this particular circuit as multi-stage amplifier, which will give you the desirable gain, which will give you the considerable high amount of gain up to that particular frequency. And after that particular frequency, your voltage gain start decreasing and decreasing. So we have to find out what is that particular frequency which will give you the attenuated amount of gain, after which we will be getting the less amount of gain. Okay, so this is been done by analyzing with AC equivalent model. So we will draw AC equivalent model. You can also draw the AC equivalent model. So just pause your screen, draw your AC equivalent model without any capacitance. We'll draw this green capacitances later on. So just draw the AC equivalent model and again come back to me. Okay, so this is particularly the AC equivalent model without any capacitances. So now we have to deal with this particular AC equivalent model, especially for high frequency analysis. So here we will write for high frequency analysis. So for high frequency analysis, we will just place few capacitances that are nothing but the intrinsic capacitances. So we'll try to place this intrinsic capacitances. So first capacitance is in between. Let us do the namakaran for each and every terminal of JFET and BJT. So this is your G1, this is your D1, and this is your S1. Okay, this is your B1, this is C1, and this is emitter 1. Okay, so now draw your capacitances in between gate and drain. Namakaran is CGD1. In between gate and your source, namakaran is CGS1. Okay, in between drain and your source, namakaran is CDS1. Simple. Similarly, at the stage 2, in between base and collector, your capacitor is CBC2, 2 for a second stage. Then another capacitance is nothing but in between base and emitter, that is CBE2. Another is in between your collector and emitter, that is CCE2. And here I will be getting the output, that is VO. Okay, as far as all the capacitances are concerned, we just have to determine how many RC networks we'll be getting, right? So here I can say that we will be getting three kind of RC network. One is at the input of first stage, in between input and output stage, and output of output stage, that is stage 2. Okay, so 3 RC network will be getting, but the problem here is this CGD1 and CBC2 are giving the complications in my complete circuit. So basically this G1 and D1 are nothing but the input and output terminal as far as only stage 1 is considered, right? So I can say that this CGD1 is connected in between input and output of stage 1. Similarly, CBC2 is connected in between input and output of stage number 2. Obviously, output of stage number 1 is nothing but the input of stage number 2. So I can say that this is nothing but the culprit capacitance which is to be replaced by using Miller's theorem, right? So first of all we will learn how to use the Miller's theorem. So using Miller's theorem. Okay, now using Miller's theorem, we just have to replace this CGD1 in between G1 and D1. Instead of that, we will draw this particular capacitance at the input side as well as output side of stage 1. Similarly, this CBC2 I will discard and I will convert at the input side of stage number 2 and output side of stage number 2. So let's try to get how we will be getting the value of CGD1? So CGD1, I will replace it at the input side as CMI1. Mi is for Miller's. So Miller's input capacitance will become 1 minus AV1 multiplied by CGD1. Okay, I'm again repeating, CMI1 is equal to 1 minus AV1 multiplied by CGD1, whereas AV1 is not equal to the gain of complete stage 1 when our signal is placed, right? So we just have to say that if this is Vy, this is your Vx, so Vy divided by Vx is nothing but the AV1. So Vy divided by Vx is nothing but the AV1. So this is your input side ka CGD1 replacement. CGD1 ka replacement at the output side is nothing but output Miller's capacitance CMO1, and that is equivalent with 1 minus AV1 inverse, not only 1 minus AV1, rather 1 minus AV1 ka inverse multiplied by CGD1. Only the change is here we have to take the inverse, right? And AV1 is same, that is nothing but Vy divided by Vx. Clear? As far as CBC2 is concerned, right? So whenever I'm using the value for replacement using CMI and CMO, that is Miller's output capacitance and Miller's input capacitance, for replacement of this CBC2, we will just say that this equation will be same, just few changes I have to make, right? So CMI2 will become 1 minus AV2 multiplied by CBC2. So instead of AV1, I will write only AV2, but here, whereas what is AV2? AV2 is nothing but, let's say, VP, and this is VQ. So I can say that here the value of AV2 is equal to VP divided by VQ. Okay. Similarly, at the output side of stage number 2, CMO2 will become 1 minus AV2 inverse multiplied by CGD2. Sorry, it's not CGD2, it's CBC2 because it's of BJT type, right? And your value of AV2 will be as it is, that is nothing but VP divided by VQ, right? So in short, we can say that we can replace this CGD1 and CBC2 once we get the value of voltage gain, that is nothing but the ratio of Vy divided by Vx and Vp divided by Vq. Okay, so for that obviously we have to deal with the DC analysis and move further for the AC analysis, and then and only then we can move further for the high frequency cutoff by using this Miller's theorem, right? So once we get this particular replacement of this particular CGD1 and CBC2 for the input and output side, I can redraw this particular circuit using 3 different independent RC networks. So 3 different RC network will be getting, with the 3 different RC network will be getting 3 different higher frequency cutoff, and with 3 different higher frequency cutoff, I will be getting concrete higher frequency for your higher frequency response. So higher cutoff frequency will be getting out of these 3 higher cutoff frequencies. So let's start with the calculation. So A part we will start, that is nothing but the at the input of stage 1. At the input of stage 1, we will be getting how many capacitances? First capacitance is CGS1, second capacitance is Miller's input capacitance, and the third capacitance will also come into picture, that is nothing but your contact capacitance, that is called as a wiring capacitance, right? So this wiring capacitance is placed in between your this, I can say that this is nothing but your wiring capacitance for stage 1, that's why I'm putting it for CWI1. similarly, output capacitance or input capacitance for your stage 1 and input capacitance for your stage 2, as far as contact capacitance is concerned, either of two you can name it, right? So I'm naming it as CWI2, input wiring capacitance for stage number 2, right? Similarly, at the output side as well, we'll be having one more capacitance, that is nothing but CWO2, that is output wiring capacitor. Here there is no input but output is there, so contact will be there at the output side. So CWO2, CWI1 and CWI2, that are three capacitances, will be there at each and every RC circuit. So starting with the first RC circuit, we'll be having one replacement of this CGD1 at the input side, this CGS1 and this CWI1 will become in parallel combination, and your circuit will look like this. This will be your R signal, this will be your RG1, right? And this will be your other capacitances. One is your CWI1, another one is your CGS1, and another one is nothing but the replacement of CGD1, that is nothing but CMI1. Okay, all these capacitances are in parallel. This is also in parallel. So this is your signal. I can say that at the higher frequency side, ultimately your fundamental frequency FH1 will be getting, that is nothing but 1 upon 2 pi RC, right? Once we get this, we just have to calculate what is C. C is nothing but the parallel combination of this, nothing but CMI1 plus CGS1 plus CWI1. Similarly, R is nothing but parallel combination. Once we get short this particular thing and we'll look from this particular all the capacitances, equivalent capacitance, we'll be getting the R signal and RG1 becomes in parallel. So R signal becomes in parallel with RG1. Okay, so this is how we'll be getting FH1. Now in the similar fashion, we will move towards the next part of the RC circuit, in between input and output stage, in between stage 1 and stage 2, or in between input and output stage. So we can say that the circuit will look like with many capacitances and many resistances as well. So RD1 will be first resistance, RB2 is first second resistance, and RPi2 is another resistance. All the resistances are connected in parallel, right? Now as far as capacitances are concerned, so many capacitances are involved in this particular RC network. One is CDS1, that is in between drain and source of stage 1, base and emitter of stage 2, this is nothing but the another capacitance placed in parallel, CWI1, CWI2 or CWO1, any one name with which we can place this particular capacitor. So CDS1, CWI2, CBE2, and the replacement of CD1 at the output side and the replacement of CBC2 at the input side, so that forms your Miller's capacitance. All these capacitances, that means 5 capacitances, will be getting, and they are in parallel combination, and all these resistances also forms the parallel combination. So let's see how the circuit will look like. This is RD1, this is your RB2. So this is RB2 in parallel with RPi2 in as far as AC analysis is concerned. So here I will write RPi2, and these three capacitances, these three resistances are placed in parallel, and along with that we will be getting all the 5 capacitances. So draw all the 5 capacitances one by one. First capacitance will be getting in between the base and the emitter, CBE2. Then we'll be getting the Miller's input capacitance, that is nothing but CMI2. Then Miller's output capacitance for the first stage, that is CMO1, and then we will draw the another capacitance as a wiring capacitance, that is nothing but CWI2, and one more capacitance is left at the first stage capacitance in between drain and source, so that is nothing but CDS1. So all these capacitances are placed in parallel along with the parallel combination of all these three resistances. So this forms a simple RC network where we'll be getting FH2 is equal to 1 upon 2 pi RC multiplied by not multiplied by FH2 is equal to 1 upon 2 pi RC where R is equal to RD1 in parallel with RB2 in parallel with R pi 2. Okay, here we have to consider if bypass capacitor is placed. If bypass capacitor is not there, we have to consider the emitter resistor into the converted to base resistor, right? So shifted emitter resistor I have to use. So that we will cover later on as when we'll take the numerical perspective. So C is equal to CBE2 plus CMI2 plus CMO1 plus CWI2 plus CDS1. Okay, so as far as all the wiring capacitances and Miller's capacitances and the stray capacitances are concerned, the addition of all the 5 capacitances, that forms your equivalent capacitance, and from that R and C value will be getting the second value of higher cutoff frequency. So I hope A and B part is very clear to you all, and then let's move to your C last part, last but not the least. C part is nothing but the output of stage 2. So output of stage 2 circuit is also very simple. So that forms the resistance, that is RC2. If load resistance is given, then we will draw load resistance RL. Okay, and then the capacitances which are placed, again these are nothing but first capacitance in between collector and emitter, that is CCE2 I can say. Then Miller's output capacitance, which is nothing but the replacement of CBC2, that is your CMO2, and the remaining is your wiring capacitor, that is nothing but CWO2. This is your complete RC circuit, comprises of 2 resistances connected in parallel combination and 3 capacitances connected also in parallel combination. So simple FH3 will be getting 1 upon 2 pi RC. R is equal to, what will be the value of R? R is equal to RC2 parallel to RL. If RL is not given, discard that value of RL, then only RC2 will be there in the value of R. Okay, so when we are taking value of C, C is nothing but CCE2 right, CCE2 plus CMO2 plus CWO2. So wiring capacitor, again if wiring capacitor is not given, then don't use that wiring capacitor, that will be 0 only, right? Simple. So use this R and C in this particular FH3 formula. You'll get to know that what will be the value of FH3. After calculation of all FH1, FH2 and FH3, question arises how to calculate the value of FH, whether we have to add, whether we have to subtract, whether we have to take the maximum value, whether we have to take the minimum value. So we have to take the FH, higher cutoff frequency, is nothing but the minimum value out of all the higher cutoff frequencies FH1, FH2 and FH3. So let's take an example. If FH1 we have got as 100 kilohertz, right, FH2 is equal to 500 kilohertz, right, and FH3 we have got as 2 megahertz. Okay, out of these 3 values, this FH1 is least value, so I can say that this particular value will give me the value of higher cutoff frequency, so that I can determine up to that particular frequency I have to operate my complete multi-stage amplifier as an amplifier. Okay, so in this particular video we have learned how to calculate the value of FH1, FH2, FH3 by using AC equivalent model, AC analysis, by using the concept of Miller's theorem, and by using the concept of the RC network and the frequency calculation. Note that your higher cutoff frequency should be minimum out of all the frequencies which we have calculated by using all the RC networks. So thank you for watching this particular video. Learn more and more EDC with me with Ekeeda videos. Subscribe all the videos of Ekeeda. Thank you so much.